Good morning. Almost done. It's the last week of classes, and it's probably not even going to be that full of a week. There are 4 lectures planned for, 4 lectures sort of in the curriculum for this week, but the last one isn't super duper necessary. It's about a thing called heap sort, and there's just nothing I could really adapt into an exam question about it, and there's not much point in teaching something that I can't evaluate. So I'm probably going to skip that one, especially if it allows for me to spend more time talking about the final exam, because that's kind of the most important part of the course, and I want everyone to be prepared for it. So basically, I'm going to go through the rest of the material in the course, excluding that heap sort thing, as quickly as possible. The quiz will still be on Thursdays, so we won't actually get any days off. But if all goes well, we'll have plenty of time to do exam review. At the end of last week, we left off talking about implementations of graphs. We had covered adjacency matrices first, where there's a matrix and the entries of that matrix represented the existence of edges between different vertices. So for example, entry 0, 1 in this matrix is 2, representing that there's a edge of weight 2 between nodes 0 and 1. And then we talked about the adjacency list. The picture kind of makes it more complicated than it has to be. Basically, the idea is just that you have a list for each vertex, and each vertex's list just lists the other vertices that it's connected to. It's really simple, and if you were inventing this yourself, you'd probably think of the adjacency list before the adjacency matrix. Even so, the visual representation of it is a bit confusing. It's very easy to confuse these linked list links for edges. Like in here, it looks like this arrow kind of makes it look like there's an edge from 4 to 8, but no, it just means that 7 is connected to both 4 and 8. And these arrows are just there because it's a linked list. Yeah?
In the case of 7, where it's connected to multiple outgoing edges,
Mm-hmm.
do we just sort them numerically, like 1, 4 goes before 8?
Ooh.
Or is there any?
I don't think any sort of sorting is needed. It might be useful if you want to tell whether a edge is connected to a specific other edge. Then having your linked list be sorted might let the search algorithm exit sooner. But the ordering of the nodes in this linked list won't result in a meaningfully different graph. But that kind of brings us to the advantages and disadvantages. Specifically, this one. To check if there is an edge from I to j, we might have to iterate through the entire length of the linked list I. So let's make this a bit more complicated. Let's make edges from 7 to 5 and also 3. So if you want to figure out whether or not 7 is connected to 3, you'd have to just traverse the linked list. Been saying this over and over in the course. Arrays provide random access, linked lists don't, so if you want to find something, you have to just go element by element. And as I was saying earlier, searching, or whether or not the linked list is sorted doesn't really matter. But if you do keep it sorted, I can totally see that leading to a slightly more efficient searching algorithm. Like, say, this is going to get a bit messy, but bear with me. I'm just going to reorder these nodes. So this is the same content as before, just sorted. And now I want to see whether 7 is connected to node 2. I guess adjacent would be a better word, but whatever. We'd start traversing the linked list, see that the first node is 3. What vertex was I talking about? I think it was 2. In any case, 3 is greater than 2. And since this list is sorted, we know that 2 must not be in the list because the first element is something that should come after it. And then the search algorithm can just exit immediately. This doesn't change the time complexity in terms of big O notation. It doesn't change the fact that the worst case of a search involves going through the entire linked list. But in examples like that, it's probably going to be faster in practice. Yeah?
In the previous option, we had done it for weighted edges. Can we implement weighted edges with the adjacency list?
Yeah, definitely. You would just need to have multiple fields, like so in a sort of standard node class, you'd have a class like this. You have your data, and you have your next. Easy. But, like, in terms of linked lists as a concept, there's nothing stopping you from having multiple pieces of data. So you could store it like that. You could also replace data with like, a pointer to a class that contains a vertex number and a weight. There are multiple ways to do this. But yeah, you'd have something like this. I'm going to replace data with something more descriptive, but otherwise keep the other. But I am going to erase this stuff because it might be misleading. So I guess that based on what I've talked about so far, adjacency lists kind of suck. If you want to pitch something, maybe don't start with the disadvantages. Adjacency lists can be useful. The main advantage is that there's no wasted space on non-existent edges. We saw earlier that in an adjacency matrix, we have to use some data on every possibility of an edge. Like 0 to 0, no edge there, but we still have to put it as 0. 0 to 1, or I guess this would be 1 to 0. Same idea. No edge, but we still have to put a 0. 2 to 0, not an edge, but we still have to put a 0. Imagine if you're making a graph for friends on a social network and the network is huge, worldwide. Most users on that network aren't going to be friends with every other user on that network, but you're going to spend a ton of space storing the possibilities of edges anyway. Adjacency lists, thankfully, don't have that problem. There's no edge from 1 to 4, for example, but there's nothing in this data structure that actually encodes that. There's just nothing in here about an edge connecting 1 to 4. And from that, we just conclude that the edge doesn't exist. We don't need to say, yeah, this thing doesn't exist. As a side effect, iteration is more efficient. If you want to iterate over all edges that lead out of a particular node, you just go through that node's linked list. So if I want to do something for all of the nodes that 0 is adjacent to, again, for that social network metaphor, I guess before I was talking about like social networks that arise naturally in real life, but now I'm actually talking about the technology things, the websites and apps that are social networks. Anyway, say user 0 posts something and it's supposed to appear on the home pages of their followers 1 and 4, or their friends or whatever. You just have to iterate through all 2 of those items. Really compare and contrast something like this. I think this is almost the same graph. The graph on the other side doesn't have weights, but I think this is the same structure. In any case, 0 is still connected to 1 and 4. But even though we can see that with our eyes, looking at like this corner of the graph, the computer doesn't know that. It has to check, okay, is 0 followed by or friends with itself? No. Is 0 friends with 1? Yes, send that. Is 0 friends with 2? No. Is 0 friends with 3? No. Ignore the weights. I don't know what they would correspond to in a social network. But you can see what I mean, I'm sure. The wasted space in an adjacency matrix also leads to wasted time when iterating through edges. However, there are some disadvantages. Already went from 1, talking about how it's hard to check whether there's an edge between 2 specific vertices. That just arises due to the difference in random access in arrays versus linked lists. But another thing is that there's no good way, at least by default, to determine the edges that lead into a specific node. This problem is just for directed graphs, of course. But with an adjacency matrix, say I want to know what edges lead to 4, like not the edges that go from 4, but to it. In that case, I can just look at column 4, and I see rows associated with 0, 5, and 7. So that exactly corresponds to the edges with vertices that lead into this. How am I going to do this with an adjacency list? I don't know. I suppose that I can loop through every edge represented in the entire data structure and you would like look for edges that lead into a specific node. But going through every single element of that entire data structure is a huge waste of time compared to the corresponding operation on an adjacency matrix, even when you consider the wasted space due to zeros. When you're doing this, you would do one operation for every vertex, so it would be like O of n, where n is the number of vertices. But with this, you do an operation for every edge, which is probably O of n squared, according to that one assignment question. So if you're ever choosing between an adjacency list or an adjacency matrix, it'll totally depend on what operations you want to do on this. Of course, you can also just add more structure to the linked list, similar to what I talked about with just adding a weight variable to the node class. You could replace next with from and to variables. And then, like, that would kind of give you two linked lists. Like, for each node, you would store all of the outgoing edges and all the incoming edges. You would have to store a lot of redundant data because, like, this edge would be in 2's list as an outgoing edge, but it would also be in 1's list as an incoming edge. So wasted memory is still a problem. I think it would be less of a problem than with these, but I don't know. So those were the two data structures used to implement the graph ADT. Next, we're going to talk about graph traversals, and this should remind you of the traversals from assignment 4. It might even be a bit of a hint for those traversals in assignment 4 in case you're still not sure how to do those. I'm not going to explicitly make any connections, though. You'll have to go like, aha, that's the thing I'm struggling with. We're going to cover breadth first and depth search traversals of graphs. And these are both sort of generalizations of the corresponding traversals on trees. And I don't think I'm going to bother with this explanation. It'll make a lot more sense with a visual. Actually, I'm going to start with a smaller example. The breadth first traversal you know and love with trees. So again, as you probably know from the assignment, a breadth first traversal traverses every level of the tree in order. So it goes to 0, and then to 1, and to 2, 3, 4, 5, 6. Going down the tree, going to every node on each level, kind of going down the tree very slowly. And in this tree example, it was always clear where to go next, even if it might be really difficult to write an algorithm for figuring out where to go next. Because that whole explanation of going to each node at each level of the tree was able to rely on the fact that there are levels to the tree, like level 1, 2, and 3 here. Yeah. But what about graphs that aren't trees? It's sort of a convention with graph traversals to start at node 0. So we can start there. And then, not sure how I want to explain this. We're just going to have to figure out how to adapt our algorithm with trees to general graphs, because it's not really clear what levels of the tree there are. You might be tempted to go like 0, 1, 2, 3, 4, 5, 6, 7, but that would rely on like edges that don't exist. Like there's no edge going from 2 to 3 or from 5 to 6. So even though it would intuitively fit into our idea of going level by level, it wouldn't be a valid traversal of the tree. Instead, I don't want to spoil the technique just yet. Whatever, I'll just go through what order you would go in these through. We're going to sort of do our best to adapt that idea of levels by visiting all the children of 0 first. So 1 and then 6. The answer key agrees with us. And then we would sort of say that 0 is on the first level of a pretend tree, and then 1 and 6 are on the first level of, or on the second level of that tree. So on the third level of that tree will be the children of 1. 2 and 3. And then we visit the rest of the nodes on that level, which are children of 6. Just 7. And then we would keep sort of doing that, kind of constructing a tree as we go and visiting the children of each node at each level until we just sort of run out of outward edges. So next up, we would go through the edges from 2, get 4 and 5, and then I think we've completely ran out of edges, but let's say I'm going to clear these annotations. But let's say the graph also had an edge from 4 to 1. Might think to go on that one next, but we had already visited 1. So we would sort of ignore that edge. I'm going to try to draw this like a tree and see if this makes it any more sensible. I don't know how it'll turn out, so if it looks weird, I'll just erase it. So breadth first traversal of this graph will sort of treat the graph like this tree. In fact, what I just drew is called a spanning tree because it's a tree that contains all the vertices of that graph. I'm going to write sorta like. This stuff's kind of hard to explain, so I'm going to stop dilly-dallying and eventually get to talking about how this would actually be implemented. Because talking about a specific algorithm for this will be way easier for me and probably more effective for you than me just waffling about pretending something is a tree. So the first two observations we definitely already saw. The children of 0 are visited in order, so 1 goes before 6 because 1 is less than 6, rather than 6 going before 1. Then those children are visited in order. The children of the first child, and then the children of the second child. And that just keeps going and going. The algorithm continues to visit child nodes in the order that their parent nodes were encountered until all nodes have been visited. And then that last bit, there's the bombshell. An implementation of a breadth first traversal would use a queue. So what does that mean? It means that I'm going to try to get the queue notation right. I think it looks like this. I'm not telling you guys to memorize it because I haven't memorized it either. But I think it looks like this. How a breadth first traversal of a graph, you can probably adapt this to trees though, would work is that it would start at node 0. That's just sort of our arbitrary starting point. And then it would visit 0's children. I'm going to check these off to mark these as visited. But also enqueue them. So we visited 0, visited 0's children, and put 0's children in a queue. Wait. I think I got the arrows wrong. I might even just look up the earlier slides with this notation. Pardon me?
At the end it's supposed to be another.
Oh yeah, I'm writing out a stack. Thank you. And can you confirm that they go in like this direction? Cool. Right, that makes a lot more sense because we've visited the children of 0 in numerical order, 1, then 6. And then we're going to want to visit the children of each child in their numerical order. So children of 1, then children of 6. So we dequeue the node 1 from the queue and then visit all of its children. So 3, no, I didn't notice 2. 2 should be visited first because it's before 3 in numerical order. So there's kind of a bunch that you have to do for each node. Mark it as visited, add it to like your final traversal, and also enqueue it. So then 6 is next up. You'll want to dequeue it. Actually, I'm going to keep old numbers sort of visually in the queue, but cross them out. So this still represents dequeuing, like 1 and 6 are no longer in the queue, but it lets you see that 1 and 6 were formerly in the queue. So we're gonna dequeue 6, visit all of its children, which are just 7. Next up is 2. We dequeue it, visit all of its children. And then we can see, because this slide has the answer to the problem on the slide, that our traversal is now complete, but there are still a couple of elements in the queue. So, from the computer's perspective, we don't know that the traversal is over. There could still be nodes not visited or something. So we would keep going. DQ3, look at all of its outgoing edges, its children. It has an outgoing edge to 4, but because 4 is already visited, we're not going to consider 4 to be 3's child. It would be weird for 4 to appear twice in our traversal, after all. So nothing happens. Same thing occurs with 7. Same node, actually. It has an outgoing edge to 4, but 4 is not its child because we already visited it. So we just dequeue it and nothing happens. And then any algorithm that uses this technique, it would see that the queue is empty and return this string or something. Yeah. Now for depth first. While a breadth first search sort of went down or would go down a tree rather slowly while visiting every node at a given level of it, depth first just goes as deep as possible, as quickly as possible, going to 0, then 0's first child, and then that first child's first child, and then that first child's first child, until it reaches a dead end. And then it goes back, backtracks as little as it can until it finds a new path to go down and repeats. This has a lot of similarities to breadth first traversal, so make sure not to get them confused. We're going to do a depth first traversal of this graph. We're going to start from 0, because that's just sort of the convention, and then go as far down a path starting from 0 until we reach a dead end. Go as deep as possible into the graph. We have 2 outgoing edges from 0, so it's not immediately clear whether we should check out 1 first or 6. You might think that a traversal starting at 0 and then going to 6 would be just as valid as a traversal that starts from 0 and goes to 1. But it's not. I think for some use cases, it's useful to have a single objectively correct depth first traversal for a specific graph. So we impose a rule that if there are multiple outgoing edges and multiple valid next vertices, you have to choose the one that is numerically first. So between 1 and 6, we're going to choose 1 as our next node. And then starting from 1, we have a choice between 2 and 3. By the same idea, we're going to go to 2 next. From 2, we can go to 4 or to 5. Obviously, got to go to 4. And then from 4, our only option is to 5. So we go there. So we sort of just traced a path. Try and make this stand out from the graph. Yeah. We've gone as far as possible into the graph, but now we've reached a dead end. We need to backtrack a bit before we can continue traversing the graph. So I'm going to use orange to denote backtracking. This won't appear in the depth first traversal, but it is certainly part of it. We're going to go back from 5 to 4. Are there any outgoing edges from 4? No. So we have to go back again. From 4 to 2. Are there any outgoing edges from 2? Yeah, I guess. But we already visited 5. Going to 5 again would be redundant, so we don't do that. We want our traversal to only include every node once. And to illustrate that, I'm just going to check off some nodes that we visited. So we keep backtracking. From 2 back to 1. Now, does 1 have any outgoing edges to nodes that we haven't visited? Turns out, yes. From 1, we can go to 3. And from there, we've kind of reached another dead end. From 3, you can go to 4, but we've already visited that. So we're going to need to backtrack again. Go back to 1. There aren't any more nodes or any more outgoing edges from 1. So you go back to where we started with 0. And then now there are some useful edges, or there's 1, but that's enough. We're going to go to 6. Check this off because we visited it. Add it to the traversal. And then finally, from 6, we have the outgoing edges to 3, but we've already visited 3, so we skip it. And to 7, which hasn't been visited yet, so we do take that edge. And that's it. We, as humans, can tell that the traversal is over because we've visited every vertex. An algorithm would probably continue, but let's not get into that. Is there anything here that I haven't covered? not really. The main ideas here are that of going as far into the graph as possible and backtracking, and how we use the numerical order of nodes as a tiebreaker when there are multiple possible edges to go to, or go through. Be careful about this because it will apply in a quiz, probably the last quiz. Like, let's see. You could use all of these rules except the tiebreaker rule to get a traversal that goes like 0, 1, 3, 4, 5, and then so on. Would probably backtrack back to 1. This would be the beginning of a depth-first traversal that does follow most of the ideas of what we're talking about, but it applied the tiebreaker incorrectly, so it would be wrong. The real motivation behind having that tiebreaker might just be to make it so the markers can go like, is this 0, 1, 2, 4, 5, 3, 6, 7? Right. If not, wrong. But whatever the real reason is, it's what you got to do. An implementation of a depth-first traversal would use a stack. Oh, is that true? That's crazy. I'm not going to go over this. Partway through that Q example, I realized, oh crap, I'm basically giving away the answer to that one assignment question about tree traversals. And I'm not going to repeat that mistake. You've already gotten the spoiler that a depth-first traversal uses a stack, but how exactly it uses a stack? That is still for you to figure out. Spoiler alert, it works pretty much the exact same as the Q thing. However, there are some subtleties, like the order of operations, like when you visit something versus when you add a thing to the data structure. It's slightly different from the breadth-first traversal and the queue. So if you try and replicate my example exactly with a stack, that won't result in a proper depth-first traversal. You're going to need to make some small, subtle alterations to the algorithm. Gotta give you something to do. How do I go through this without spoiling breadth or depth for searches? I think I'll do this the sort of way that you would do it on a quiz, rather than how you would code it. I'm not going to bring stacks or queues into this at all. So you'll still have to figure out those stack and queue details yourself, but this is a good example of what you'll be asked to do on a quiz or on the final. Whew. So, breadth-first search. We're going to start from 0, obviously. And then we're going to visit all the children of 0 in order. So I see 2 outgoing edges. Writing 0, 4, 3 would be wrong. I go 0, 3, 4. And I'm going to mark these as visited. And then we check out the children of those children. We're going to do 3 first, because it's first in numerical order. Indeed, if you were programming this and using a queue, 3 would be the first to be dequeued. There's nothing we could do from here, actually. Oh, I didn't notice this guy. We can totally go to node 2 from here. But that's it. If you're doing this on paper, it might be useful to label like the level of the breadth first search they're at, or maybe their order in the queue. But I'm just going to keep track of it in my head. 4 must be the next one. We see outgoing edges to 5 and to 6. So let's add them to the traversal and mark them as visited. And then to 2, or from 2, there's an edge going to 1. So we visit that, add it to the traversal. Then rapidly starting to lose track of this, but I can remember that we're basically going through all these nodes in order. Last one we checked was 2, I think. Went to 1. And then 5 is next. Its only outgoing edge goes to 2. So we kind of ignore it. Then 6, that has an outgoing edge to 7. And then we can see that we're done. We've checked off every node in the graph. But if you were a computer executing an algorithm, you would check 1, find that it has no outgoing edges, and then 7, and find that it only has 2 outgoing edges, but they both lead to nodes that we've already visited. Cool. Now let's go depth first. We're going to start at 0 because I said so. The person who made the curriculum said so. And then we're going to go as far down a path from 0 as possible before backtracking. So from 0, we could go to either 3 or 4. We choose 3 because it's numerically first. And then, almost missed this a second time, we have an outgoing edge to 4, but we also have one going to 2. So we go there because it's numerically first. And from 2, the obvious choice is to go to 1. We also could have gone to 4, but that 4 would have been greater than 1, so it would have been incorrect. I'm going to bring out the colors again. So you went on the path 0, 3, 2, 1. We hit a dead end, so we're going to backtrack, but only as far as necessary for us to be able to go down a different path. And it turns out we don't have to do much backtracking at all. We backtracked to 2, and then right there is another outgoing edge going to 4. We're going to take that and then an outgoing edge to 5. Mark both of those as visited. And add them both to the traversal. Now from 5, we've hit a dead end. There is an outgoing edge to 2, but that would be bad, stupid, dumb to take because we already visited 2. So we backtrack. And again, we don't have to do that much backtracking because at 4, there's already an outgoing edge going to 6. And from there, an outgoing edge going to 7. And it looks like we're done. So that's how you do breadth first search and a depth first search. For a depth first search, feel free to draw on the graph and just keep track yourself of which parts of the traversal are actually moving through it and appearing in the final answer, and which parts are backtracking. There's also no rule that says you can't bring colored pencils to a quiz, so you might want to do that. But this approach requires keeping a lot in your head at the same time. You might want to draw an extra thing to the side that lets you keep track of which nodes you visited and which ones to backtrack to and how. Perhaps even a data structure. Like this. So I've already shown you how to use cues for a breadth first traversal, and you know that you're going to somehow use stacks for a depth first traversal. And again, I'm not going to show you how to use a stack for a depth first traversal, but you're kind of going to have to by this Friday because of the assignment due date. And if you figured it out by Thursday morning with the quiz, I honestly recommend just drawing a stack for depth first and key for breadth first on your quiz paper to help you keep track. To help you keep track of which nodes you visited and how to backtrack. I'm going to keep this annotation because it's a useful visual of what the depth first search is doing. These 2 slides aren't very notable. I did the things that I wrote down. And that's it for graph traversals. So that is the end of the lecture that was slated for today, but as I've been talking about, it's nice to get ahead. I want to keep the I want to attempt to move the cutoff date for the quiz as far back as possible. So let's keep going. We're going to talk about shortest path algorithms to round out our discussion on graphs. This is like a super practical application of graphs because, you probably used it at least once to get to university. Like using graphs to model transportation, where the vertices are buildings and the edges are roads between them. A shortest path algorithm can help you find the most efficient route from one place or the other. Something that tends to be useful. If the graph is unweighted, then finding the shortest path is actually really simple. It's the path with the fewest edges. And to find the shortest path, you just need to start at a specific node and do a breadth first traversal until the second node is visited. For example, let's see. I want to find an example of a pair of nodes where there are 2 possible paths there and one of them is inefficient. Like, it has too many edges. And then I want to show you that you can find the efficient one, the path with the fewest edges, by doing a breadth first search. So how are we going to do that? Okay, let's say I want to go from 0 to 5. And my best guess at how to do so is to go from 0 to 3 to 4 to 6 to 7, back to 4. I'm very stupid. And then to 5. Actually, let's make this a bit less egregiously bad, a bit less contrived. Say that I genuinely thought this was the shortest path from 0 to 5. But I can probably do better with a smarter algorithm. So if I do a breadth first search, or this is equivalent to breadth first traversal, you could use the names interchangeably. You would just traverse the graph 0, 3, 4, 2, 5. We found 5. And then, this isn't immediately useful looking. Whoop-de-doo, we know that 5 exists. How does that give us a shorter path? Well, if your search keeps track of what node each node was visited from, you could sort of backtrack that to reverse engineer a shorter path. So we found 5. We know that we got there from 4. So where did we get to 4 from? Well, 4 is right there. We got that from 0. So the shortest path is 0 to 4 to 5. And you could see that the path exists. It's just two edges. Much nicer than our 1, 2, 3, 4, 5 edge path that we made from our first guess. I'm just going to reiterate this because it's actually going to be important for our more complicated algorithm. We did a search for vertices while keeping track of where we got to each vertex from. Our destination was 5. We knew that we got there from 4. So we check how we got to 4. It was from 0. So going backwards, 5, 4, 0, gives us the shortest path, 0, 4, 5. Cool. But what if the edges were weighted? What if this edge had weight 10, this edge had weight 10, this edge had weight 10, this edge has weight 15 to mix it up, but this one has weight 10 as well, making it so the weight of our long path is 1, 2, 3, 4, 5, 55. And then this edge has weight, 2, but this edge has a weight that is 1 with an untold amount of zeros after it. A truly humongous number. There is technically a direct connection from 4 to 5, but you're better off just taking a more indirect route. In this case, the so-called long path has weight 55. You could imagine this being a transportation thing, and maybe 2 cities have 55 kilometers between them. And then the seemingly shortest path in terms of number of edges is like a Googleplex. No, that's definitely not a Googleplex. Maybe approaching a Google. It's a big number. So we need an algorithm that will somehow take the edge weights into account and recognize that sometimes the path with more edges in it is better, say cheaper, than a seemingly more direct route. Ooh, this is going to be fun. Which brings us to Dijkstra's algorithm. I still have trouble spelling Dijkstra. This is an algorithm for finding the shortest path from a given node to another node in a weighted graph. Weighted graph specifically. We saw that with unweighted graphs, you don't really need to worry about the, what am I saying? You do need to worry about stuff. We saw earlier that for unweighted graphs, there's a really simple algorithm. We're going to do this example with directed graphs, but Dijkstra's algorithm also applies to undirected graphs. Undirected graphs might show up on the quiz or the exam. So suppose we wanted to find the path from, or shortest path from node 0 to some other node in the graph. The exact destination doesn't actually matter because Dijkstra's algorithm actually ends up finding the shortest path from node 0 to every other node in the graph. I'm not sure if it's possible to make a more efficient version that just finds a specific, or a path between two specific nodes. Dijkstra's algorithm just does the whole thing. You're going to make a table with one column for each node and 3 rows, cost, previous, and done. First column contains the starting point. Not sure how much I'm going to want to annotate this and how much I'm going to want to scroll through because this has useful directions. I think I'm going to flip between slides, talk about the directions and then go back to annotate this. Then I'll erase it all to avoid spoilers. So the cost to get from the starting point to itself is 0. You are already at your current location. But for all the other destinations, we don't know how long the shortest path to them is. And our algorithm is going to depend on some less than comparisons. So we're going to initialize those entries to infinity so that when we find any number for the length of the shortest path, it'll show up as less than the current cost. And then we also have a row for the previous node for each node. This is going to play the same role as these from things from the simpler algorithm. But at the beginning of the algorithm, it doesn't really make sense to put anything there. There is no previous node from 0, and also no sensible previous node to any of the other vertices. And finally, our done row, we're going to put false in every column Because we're not done any of these. As we go through the algorithm, we're going to mark these as true once we've found the shortest path from 0 to a specific one. And then when all of these entries are set to true, then we're done. Now that I explained that, it seems pretty obvious that you can actually make a slightly more efficient version of Dijkstra's algorithm that finds the shortest path from a specific node to one other specific node. But it'll still involve finding the shortest paths of other vertices along the way. You can just stop the algorithm once the column you're trying to find the shortest path for the node of becomes false. Sorry, becomes true. Okay, so this is our initial setup. The distance from 0 to itself is 0, but the distance to everything else is infinity, and nothing is finalized. So we're going to go through several iterations of basically a loop. Of all the nodes that are not done, find the one with the smallest cost and flag it as done. In our first iteration, that's going to be 0. So we mark this as true. Mark the done row for that column as true. So call this node x. For now, in our first iteration, x is 0. And then for every edge from x to another node, call whichever node you're thinking of currently y. Calculate the current cost of x plus the weight of the edge leading to y. And if the result is less than the cost of y, update the cost of y to that value and update y's previous node to x. So for our example, again, you've got edges to 1, 2, and 3, and we're going to update those. So to 1, we see there's an edge with weight 30, and adding that to the cost to node 0, we still end up with 30. Is 30 less than infinity? Sure is. So we update this accordingly. We do the same thing with the other two edges that we found. So we found that from 0, we can reach 1 with cost 30, 2 with cost 10, and 3 with cost 100. Keep thinking of transportation here. There are roads between cities 0 to 1, 0 to 2, and 0 to 3, and they're like 30, 10, and 100 kilometers each. And again, for these, we update the previous row. For each of these, we got there from node 0. So we say that the previous node for all of these is node 0. So that's the result of iteration 1. We've flagged node 0 as done and updated data for nodes 1, 2, and 3. And then at this point, we kind of know exactly how to do the rest of the algorithm. We're just going to repeat all the steps that we've seen before. So iteration 2, first step is to find the node with the least cost. That is 2, because 10 is less than 30 and 100. We're going to mark that as done, and then update other columns' information using the outgoing edges of 2. We see that 2's only outgoing edge leads to 4 and has weight 50. So we're going to update 4. You might be tempted to write 50 here. And like, you probably could get by on doing this if you have a slightly different algorithm for calculating the cost of the path later. But what we're going to do for this class is, actually, writing 50 here, like just writing the weight of the edge to its previous one, would totally screw this up, so don't do it. So instead, we're going to write the weight of the total path from 0 to this node, 4, which is this edge of weight 10 plus this edge of weight 50 for a total weight of 60. We got to 4 from 2, so we say that its previous node is 2. And then we keep doing that. I'll probably have to stop the lecture in the middle of this, but I'm going to go right to time. Smallest weight is node 1. 30 is the smallest of the numbers in the cost row that isn't already marked as done. And also, I'll take a moment to highlight that when you're at this step of the algorithm, the lowest number in the cost row that isn't already marked as done is actually the weight of the shortest path to that node. You'll never be able to improve on, like in this case, weight 30 to 1. And the reasons why aren't super clear, but have been proven mathematically. You'll learn more about that in Comp 2080. I believe that course talks about proofs of correctness. But for now, trust me, bro, this just works. We're going to mark 1 as done. Check all the outgoing edges from 1 and update nodes data accordingly. So to 3, we have 30 and 60, a weight of 90. This is less than 100, so we're going to update that. We've shortened the shortest path a bit, and we're also going to update pre, because now the shortest path that we found so far to node 3 involves going to 1 and then to 3. So 3's previous node will be 1. Next is to observe the edge from 1 to 4, weight 20, and then do the rest of the iterations for nodes 3 and 4. But I have like 5 seconds left, so we're just going to continue this next class. See you tomorrow.